Hello everyone, welcome to Free Math and welcome to our journey of class 10th mathematics, and I'll be your guide. So class 10th is a pretty crucial year and it is important that you ace your board exams and prepare yourselves for the future. So we'll kickstart with the first chapter, the real numbers. It's a pretty relatively easy topic compared to the other chapters from 10th grade. And don't worry if math feels challenging, it's okay. So we'll practice many problems and enough examples. So the aim of this playlist is to cover the entirety of CBSE NCERT problems and all the exercise questions and all the examples. Okay, so let's start with the very first concept. So let's start with the chapter. So let's recall what are prime numbers. So I think we must have learned this in 6th grade, I believe. What are prime numbers? And what are composite numbers? So what is a prime number? A prime number is a natural number greater than 1 that has only two factors, 1 and itself. Can you give me an example? For example, 5. What are the factors of 5? The factors of 5 are 1 and itself. The factors for 11, it's 1 and 11 itself. So these are prime numbers. Yeah. What is the smallest prime number? The smallest prime number, that would be 2, right? Because the only factors of 2 are 1 and 2 itself. Now, is 1 a prime number? No, it's not, because a prime number and a composite number both are greater than 1. That's pretty important. So 1 is neither prime nor composite. Okay, and 2 happens to be the only even number. So these are basic concepts that you must have learned in earlier grades. And coming to a composite number, what is a composite number? A composite number is also a natural number greater than 1 that has more than two factors. Okay, more than two factors. For example, let's take 8. So what are the factors of 8? 1, 2, 4, and 8 itself. So it has more than two factors, right? For example, 9. What are the factors of 9? 1, 3, 9. So it has more than two factors, correct? What is the smallest composite number? The smallest composite number, that would be, 1 is neither prime nor composite, 2 is a prime, 3 is also a prime. Now next comes 4. So 4 is the smallest composite number because it has two factors. It has more than two factors, 1, 2, 4. It has three factors. Okay, so this is just a quick recall from our earlier grades. Now let's come to the very first theorem of real numbers, the fundamental theorem of arithmetic. So this is central to a topic of math called the number theory, which you'll learn later if you try to pursue mathematics. Anyway, so here we don't have any proof, but let's state the theorem. So the fundamental theorem of arithmetic says every composite number, so let me try to highlight that, every composite number can be expressed as a product of primes, and this factorization is unique. So let me highlight that unique part in a different color. Okay, probably not blue. Let me try orange perhaps. Yeah, this is better. Yeah, so every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. So let's understand this statement. It says that if you take any composite number, for example 12, it can be written as a product of primes. So 2 into 2 into 3. So these are all primes. So we can write 12 as a product of primes. And this factorization is unique. So apart from the order in which the prime factors occur. So you can perhaps write it in a different order like this, but that doesn't matter. The factors are unique. The prime factors are unique, correct? We can take any composite number. For example, let's take 100. 100 is 25 times 4, which is 5 squared times 4, which is 5 into 5 into 2, right? So every composite number can be written as a product of primes, and this factorization is unique. Okay, so that is the first. So this is the first theorem. Okay, the fundamental theorem of arithmetic. Okay, so and let me repeat: the prime factorization is always unique. Yeah, this is a pretty important point. The prime factorization of a natural number is always unique, except for the order of its factors. Okay, now before we start doing some problems, let us once again recall the divisibility rules which we have learned in 6th grade. Yeah, 6th or 7th. I think it's 6th grade. Yeah. So let's start with the divisibility test for 2. When is a number divisible by 2? If it ends with these digits. For example, 58 ends with 8, so it is divisible by 2. Now the divisibility test for 3. When is a number divisible by 3? If the sum of digits in number is divisible by 3, then the entire number is divisible by 3. For example, what do you think? 383. Is it divisible by 3? So let's check. 3 plus 8 plus 3, that would be 3 plus 8, 9, 10, 11. 11 plus 3 is 14, and 14 is not a multiple of 3. So 383 is not divisible by 3. Let's check another number. What about 189? 189, is it divisible by 3? So we have 1 plus 8 plus 9. 1 plus 8 is 9. 9 plus 9, 18. Yes, 18 is a multiple of 3. So 189 is indeed divisible by 3. Okay. Now what about the divisibility test for 4? When is a number divisible by 4? If the last 2 digits of a number is divisible by 4, then the number will be divisible by 4. For example, we can go with 1936. Yeah, is this number divisible by 4? Yes, it is. Why? Because the last 2 digits, 36, is a multiple of 4, right? 4 nines are 36. So this number is divisible by 4. Now coming to divisibility test for 5, that's pretty easy. If the last digit of a number is either 0 or 5, then the number is divisible by 5. What about the divisibility test for 6? So in order for a number to be divisible by 6, it should be divisible by 2 as well as 3. Okay. So for example, 189 we saw earlier. It was divisible by 3, but it is not divisible by 2. So this number is not divisible by 6. Yeah, 189 is not divisible by 6. Let's take another example. Let's look at 336. Okay, is this number divisible by 2? Yes. Is this number divisible by 3? Let's check. 3 plus 3 plus 6, 6 plus 6, 12. Yes. So that means this 12 is equal to 12, so this number is divisible by 3. So since it is divisible by both 2 and 3, it is divisible by 6. So 336 is indeed divisible by 6. Okay, fine. Now let's come to divisibility rule for 7. Sometimes it is, let me read the statement. The divisibility rule for 7 states that for a number to be divisible by 7, the last digit of the given number should be multiplied by 2 and then subtracted with the rest of the number, leaving the last digit. If the difference is 0 or a multiple of 7, then it is divisible by 7. Now it's kind of confusing, this pretty lengthy statement. Sometimes you might think, okay, it is better to divide by 7 and see it for yourself. And I would agree, yeah. Okay, but let me just tell you how to do the divisibility test for 7 if this is too boring to read. So for example, let me take a number like 441. So it says the last digit of the given number should be multiplied by 2. So the last digit is 1. It should be multiplied by 2. So we'll get 2. And then subtracted with the rest of the number, leaving the last digit. So the rest of the number leaving the last digit is 44. And we should subtract this product from that. So 44 minus 2 is 42. Now, if this difference is a multiple of 7, then it is divisible by 7. So 42 is a multiple of 7. So therefore 441 is also divisible by 7. Okay. Do you want another example? Okay, let me give you another one. Let's try 672. Let's try 672. So we'll take the last digit multiplied by 2. So the product is 4. Then we'll take the remaining digit 67 and then subtract the product from it. So 67 minus 4 is 63. And guess what? This is a multiple of 7. 7 nines are 63. So therefore 672 is also a multiple of 7. Okay. So I hope it is clear. Okay. So these are the divisibility rules until 7. What about the divisibility rule for 8? If a number with 4 or more digits is divisible by 8, then the number, if the number formed by the last 3 digits is divisible by 8, then the number is divisible by 8. For example, let's take let's see, for example, let me try to think of a good example. 54,490. Okay, not this. Let me look for another one. Okay. What about 5056? So is this number divisible by 8? So let's take a look at the last three digits, which is 56 basically. 56 is a multiple of 8. 8 sevens are 56. So therefore, this number is also divisible by 8. So for divisibility rule for 8, we have to check the last three digits, right? Okay. And if we just have 1 or 2 or 3 digits, then we have to check it by actual division. Okay. Now coming to divisibility rule for 9, it is once again like 3. If the sum of the digits is divisible by 9, then the number is divisible by 9. For example, we can take 801. Okay, is this number divisible by 9? It is, because 8 plus 0 plus 1 is equal to 9, which is divisible by 9. Okay. So let me erase everything. Coming to 10, 10 is pretty easy. Now coming to 11, which is very important. If the difference between the sum of digits at odd places and even places is either 0 or a multiple of 11, then the entire number will be divisible by 11. So let me give you an example. Consider the number 6952. Okay. So first what we're going to do is, let's take a look at these numbers. 6 plus 5, add it, we'll get 11. Then we'll take the alternating digits. 9 plus 2, we'll get 11. Then we'll form the difference between them. Okay, 11 minus 11 is 0, right? So if the difference is 0 or a multiple of 11, then the number is divisible by 11. So 6952 is indeed divisible by 11. And let me give you another example. 8679. Wait, let me think of a bigger number. 86856. Okay. Now let's form the alternating sum of digits. 8 plus 8 plus 6. That would be 22. And what about the other one? 6 plus 5. That's 11. And 22 minus 11 is 11, which is a multiple of 11. So 86,856 is indeed divisible by 11. Okay. So these are the divisibility rules. So now this would help us in factorization. So all of this you could have skipped if you knew the divisibility part. So anyway, let's proceed to another skill. So another skill that you need to remember is the multiplication table. Okay, which I would recommend you learn up until 20. Okay, up until 20, and it is pretty important to memorize, especially the prime, the table of prime numbers. For example, 17 table, 13 table, 19 table. So because these numbers, for example, when you look at the number 171, it should immediately come to your mind, oh, it's 19 times 9. Or for example, if you see the number 117, you should immediately be able to say it's 13 times 9 and so forth. Okay. Another important skill is the square and cube table. So it is important to memorize the squares and cubes. And also these two are miscellaneous. 23 squared, 29 squared is 841. And also the cubic part. It would be very nice if you remember these cubes and squares, and especially the primes. Okay. And we have another skill which is kind of hard to master. It is all memorization, but this is also important. Okay, the product of a random product of primes. Okay, 11 times 19 is 209. 19 times 29 is 551. 17 times 29 is 493. 17 times 19 is 323. So the moment you see these numbers, you should be able to recognize the product of primes. Okay, so here we had taken 2 primes. Here we are taking 3 primes. So it would be nice if you try and memorize these products. Okay, so it takes a little bit of memory, memory training. Okay, so I think this is one of the exercise questions, that 7,249 is 17 times 19 times 23. So as I said, it is pretty important to memorize um, um, all these products. So we have 4 important skills, starting with the divisibility rules, then the multiplication table, then the square table, cube table, and then finally this miscellaneous product of primes. Okay. So finally, let's start with our exercise questions. Okay, so we have spent 15 minutes on uh, the basic skills. Now we are starting the chapter. Okay, so first question, express each number as a product of primes. So 140, so let's go back to prime factorization. So 140, it is divisible by 2. So 2 times 70, now 2 times 35, 5 times 7, 7 times 1. So 140 can be written as 2 squared times 5 times 7. Coming to the next number, 156. So once again, divisible by 2, again divisible by 2. Now coming to 39. 39 is divisible by which number? 39 is divisible by 3 plus 9, which is 12. It is divisible by 3. And if you know the multiplication table, it's 3 times 13. Okay, so you should be able to memorize all that. So 156 is 2 squared times 3 times 13. Okay, coming to a bigger number, 3,825. So it's divisible by 5, 5 again. What about 153? It's not divisible by 2. Is it divisible by 3? It is, because 1 plus 5 plus 3 is 9. Yeah. And 51, once again divisible by 3. 5 plus 1 is 6, multiple of 3. So 3 times 17 is 51. Okay. Next question, 5005. So this number, it definitely looks divisible by 5, but it is also divisible by 11. Why is it divisible by 11? Because if you look at the alternating sum, 5 plus 0 is 5, 0 plus 5 is 5, and if you take the difference, 5 minus 5, that is equal to 0. So this number checks the divisibility test for 11. So we can divide by 11, a bigger number. Now 455 you can divide with 5. And coming to 91, if you recall the multiplication table, it is 13 times 7. So once again, so that's why I said it is pretty important. It is very important to memorize the multiplication table of prime numbers. Okay, very important skill. Okay, 7429. Now if you recall, I had already warned you about this number. Yeah. This is a product of 3 primes, 7429. It is 17 times 19 times 23. Okay, so it would be handy if you go back and master those skills. The first 15 minutes of the lecture, just go back and have a good look at it. Take a screenshot if you want. Go back to those important skills. Okay. Okay, fine. Now we are coming to, so we are done with prime factorization. Now let's come to a very important topic. Perhaps this is central to this chapter, the highest common factor and the lowest common multiple. So this, you must have learned it in lower grades, in 6th grade perhaps. What do we mean by highest common factor and lowest common multiple? So let me just discuss what does that mean. So this stands for highest common factor. Okay, highest common factor. So let's take, for example, two numbers, 20 and 25. I have two numbers. So what are the factors of 20? 1, 2, 4, 5, 10, and 20. What are the factors of 25? 1, 5, and 25 itself. So what are the common factors? What are the common factors? The common factors are 1 and 5. That's it, right? These are the common factors. And what is the highest, whoops, spelling. What is the highest common factor of 20 and 25? That would be 5, because among the common factors, 5 is the biggest, 5 is the highest. So that is what we mean by highest common factor. I hope it's clear. Let me erase this. Now coming to lowest common multiples. Lowest common multiple singular. Okay, erased. Okay, what do we mean by LCM? LCM is lowest common multiple. Okay, for example, let me take two numbers, 6 and let's say 8. Okay, what are the multiples of 6? The multiples of 6 are 6 1s are 6, 6 2s are 12, 6 3s are 18, 6 4s are 24, 6 5s are 30, 6 6 are 36, and we have infinitely many. What are the multiples of 8? 8 1s are 8, 8 2s are 16, 8 3s are 24, 8 4s are 32, 8 5s are 40, correct? Yeah. So, and it keeps on going. Yeah. So, do you see any common multiple here? Yes, 24. Yeah. And turns out this is the lowest common multiple because we don't have any other common multiple which is lower than 24, right? There could be infinitely many common multiples, but 24 happens to be the lowest of the common multiples. Yeah. So that is what we mean by LCM. LCM is the lowest of the common multiples. So once again, this is just a recap of 6th grade. If you already know this, you can skip this part. Okay, but don't skip right now. Now we are coming to the definition of HCF and LCM. So let me first define how to find HCF and LCM using prime factorization technique. So HCF is the product of the smallest power of each common prime factor in the numbers. For example, let me take two numbers 20 and 25. So if you prime factorize 20, it is 2 times 2 times 5. If you prime factorize 5, it is 5 square. Yeah, 5 into 5. 5 into 5, which is 5 square. Here this is 2 into 2 into 5, which is 2 square into 5. Now how do I find the HCF of 20 and 25? I have to look for the product of the smallest power of each common prime factor. First of all, I'll have to look at the common prime factor. So what is the common prime factor? 5 is a common prime factor. So first I'll write 5. Okay. Now I have to write the smallest power. So in 5 and 5 square, which is the smallest power? Smallest power is 1. Okay. And I have to form the product. So here it is just 5. So HCF is 5. Okay. Let's take a look at another example. Let me try to give a very big number. Suppose I have a number which is 2 squared into 3 into 5 to the power 4. I have another number which is 2 to the power 7 times 3 squared times 5 squared. So I have two numbers, A and B. Yeah. So what do you think is the HCF of A and B? So once again, first we have to look for the common prime factors. So common prime factors are 2, 3 and 5. So all of them are common. So let's write 2, 3, 5. And we have to write their smallest powers. So smallest power of 2 is 2, so 2 squared. Smallest power of 3 is 1, so 3 to the power 1. Smallest power of 5 is 2, so we can write 2, 5 squared. And then we form what? We form the product. So the product of the smallest power, so 2 squared into 3 into 5 squared. So that will be the HCF of A and B. Yeah. Now coming to LCM. Let's come to LCM. It is the product of the greatest power of each prime factor. So for example, if I have two numbers, which is 2 cubed into 3 squared, I have another number, which is 2 into 5 times 7 squared. Now what will be the LCM of A and B? So we have to form the product of the greatest power of each prime factor. So which means we have to write all the prime factors 2, 3, 5, 7. We wrote all 2, 3, 5, 7. And we have to write their respective greatest powers. For example, for 2, 3 is the biggest power. For 3, 2 is the biggest power. For 5, it is 1. And for 7, it is 2. And we form the product. Okay. So that will be the LCM of these two numbers. Okay. So now let's take a look at the examples. Let's take a look at the examples. Oh, before we go into example, we have a very important concept, very important concept, This concept is a frequent 1-mark question or sometimes even 3-mark question. It turns out that the HCF of two numbers and you multiply it with the LCM of two numbers, always it turns out it is equal to the product of the two numbers. Okay, let's see how. Let's look at the first question. Suppose you have two numbers, 26 and 91. So find the LCM and HCF of the following pairs of integers and verify that LCM times HCF is equal to product of two numbers. So we're going to do it the prime factorization way to find the LCM and HCF. So let's start with 26. 26 is 2 times 13 and 91 is 7 times 13. So we expressed it as a product of primes. Now let's start with the HCF. So HCF, once again, it is a product of the smallest power of each common prime factor. So which one is the common prime factor? It is 13 and the smallest power is 1. So therefore the HCF is 13. Okay. What about the LCM? LCM is the product of the greatest power of each prime factor. So we have 3 prime factors, 2, 7 and 13, and their greatest powers are 1 itself. So we just have to multiply them. We'll get 182. So we found the HCF and LCM of 26 and 91. Now we have to verify. So what do we mean by verify? Verify means you have to prove that LHS is equal to RHS. So we'll start with LHS. So LHS is LCM times HCF. So LCM is 182, HCF is 13. So 182 times 13, which is equal to 2366. Okay. Now let's start with RHS. RHS is product of two numbers, which is 26 times 91. 26 times 91, that is equal to 2366. So hence LHS equals RHS, hence verified. Yeah. So this is what you should be doing in verification questions. Let's take a look at another example. 510 and 92. So 510, let's start prime factorizing. So 5 times 102, 3 times 34, 2 times 17, 17 times 1. Okay. So 510, 510 is written as a product of primes. Now coming to 92, 2 times 46, 2 times 23, 23 times 1. So 92 is 2 squared times 23. So once again, HCF is the product of smallest power of each common prime factor. So which are the common prime factor? Turns out we only have 2 and we write the smallest power, which is 2, right? So 2 is the smallest power. Now coming to LCM, it is a product of the greatest power of each prime factor. So we have to write all the prime factors and then write their respective powers, greatest powers, and then multiply. Yeah. So it is 2 squared into 3 into 5 into 17 into 23, which happens to be 23,460. Now let's come to the verification part, because the question is asking us to verify that LCM times HCF is equal to product of the two numbers. So LCM times HCF, LCM is 23,460, HCF is 2, let's multiply, we get 46,920. Now coming to the RHS, product of two numbers, which is 510 times 92, turns out, sorry, once again it is 46,920, hence verified. Another question, 336 and 54, let's start prime factorizing. 3 times, 2 times, 2 times, 2 times, 2 times, and 7. Sorry. Okay. So 54 is 3 times 18, 3 times 6, 3 times 2, 2 times 1. So 54 is 2 times 3 cubed. Now let's find the HCF, which is the product of smallest power of each common prime factor. So HCF is 2 times 3, which is 6. And LCM is the product of the greatest power of each prime factor. So we have to multiply 2 cube, 3 cube, and 7, which is 8 times 9 times 7, which is 3024. So let's verify it real quick. So LCM times HCF is the product of these two, which is 18,144, and the product of two numbers is 336 times 54, which is once again 18,144. So hence verified. Okay, so we are done with the verification questions. Now here we have three numbers. The third question: find the LCM and HCF of the following integers by applying the prime factorization method. So let's start with the prime factorization of each of the numbers. So 12 is, that's pretty easy. 15 is also easy, 3 times 5. 21 is 3 times 7. Okay, so once again, HCF, we have to take the smallest power of each common prime factor and then multiply them. So which is the common prime factor? Common prime factor, it happens to be 3, right? Be careful. 3 is the only common prime factor. So therefore the HCF is 3. Now coming to LCM, we have to take each prime factor and form the product of their greatest powers. So for 2, the greatest power is 2 square. For 3, it's 3 itself. For 5 and 7, it's the power is 1. So we just have to multiply them all. We get 420. Nice. Okay. And one more thing which I wanted to say was HCF of ABC times LCM of ABC is not necessarily equal to the product, okay? Because here we have 3 numbers, yeah? But if you have 2 numbers, yes, we have solved enough examples, yeah? We have solved enough examples where this is true, but this is not true, okay? So be very careful, yeah? Be very careful. Okay, let's do this question now. Now here we have 3 numbers, 17, 23, and 29. Let's start. So 17, 23, and 29 are prime numbers, so their prime factorization would be the number itself. So HCF would therefore be just 1 because we don't have any common factor apart from 1. Yeah. And LCM would obviously be the product. And if you recall, 17 times 23 times 29 is 11,339. Of course, you can multiply it and see it for yourself. Or if you remember the skill which I had told, the 4th skill, the miscellaneous product of primes, you could have written it straight away. Yeah. Okay. 8, 9, and 25. So 8 is 2 cubed, 9 is 3 squared, 25 is 5 squared. Once again, here for HCF, we need a common prime factor. So here the common prime factor, there are no common prime factors. So the only prime factor is 1, right? So HCF is 1. Yeah. And what about the LCM? LCM, we're going to have to multiply everything here, which is 2 cubed into 3 squared into 5 squared, which is 1800. Okay, now let's come to this question. Here it is given that HCF of 2 numbers, 306 and 657, is equal to 9, and the LCM of 2 numbers, 306, of the very same 2 numbers is what we have to find. Okay, it is not given, that is what we have to find. Now, which property will you use? So they are not expecting us to solve the problem by prime factorization. They are in fact expecting us to use this property. We know that the product of 2 numbers is equal to the HCF times the LCM. So HCF is given to be equal to 9, right? And the numbers are 306 and 657. So we can just plug in the values, right? So therefore the LCM, we can transpose 9 over to the other side, and we can cancel. 9 ones are 9 times 34. Now 34 times 657 is 22,338. So that would be the LCM. So just by making use of this property, we found out the LCM without using the prime factorization technique. Yeah? Okay, interesting question. 5th question. Check whether 6 to the power n can end with the digit 0 for any natural number n. Okay, so like they're asking us whether 6 square or 6 cube or 6 to the power 56 or 6 to the power 97 will any of these numbers, can it end with 0? For example, 6 squared is 36. It is ending with 6. 6 cube is 216. It is ending with 6. So is there a possibility for 6 to the power n to end with 0? That is what they're asking. Yeah. Now let's observe one thing. If a number has to end with 0, it has to have 5 as one of its prime factors, right? Because if you take a number like 150, it is divisible by 5. Yeah. So if a number has to end with 0, 5 should be a prime factor, correct? 5 should be a prime factor. And for any natural number n, 6 to the power n can be written as 2 times 3 to the power n. Yeah, because 6 is 2 into 3, which means you can write it as 2 to the power n times 3 to the power n. But guess what we have done? We have written 6 to the power n as what? As product of primes, right? And do you recall the very first theorem that we learned in this chapter? We learned the fundamental theorem of arithmetic, which states that any prime, any composite number can be written as a product of primes. So here we have written 6 to the power n as a product of primes, correct? Fine. So how does that help? Do you remember, but while we talked about the fundamental theorem of arithmetic, we had emphasized on the uniqueness, right? Which means that if 2 and 3 are the only prime factors, then we cannot have another prime factor, right? So 2 and 3 are the only prime factors, which means there are no other primes in this factorization. So can 5 be one of the prime factors of 6 to the power n? Definitely not, because there are no other primes. The only primes are 2 and 3. Yeah. So since 5 is not a factor of 6 to the power n, that means 6 to the power n cannot end with the digit 0. It cannot, simply cannot end, because the uniqueness of the fundamental theorem of arithmetic guarantees that there are no other prime factors apart from 2 and 3. Okay. So this is an interesting conceptual question. Okay, let's take a look at the 6th question. Explain why 7 times 11 times 13 plus 13 and 7 times 6 times 5 times 4 times 3 times 2 times 1 plus 5 are composite numbers. So once again, let us recall what are composite numbers. It has more than 2 factors. Yeah, more than 2 factors. It is composite numbers are numbers, natural numbers greater than 1, having more than 2 factors. Now, if you look at, so let's take a look at the very first number. Let's analyze this number. Do you think it has more than 2 factors? If you notice, 13 is from these two terms. From these two terms, we can perhaps pull out 13. Yeah. So if you pull out 13, you'll get 7 times 11 plus 1, which is 13 times 77 plus 1, which is 78. So what does it mean? Whatever this number is, we wrote it as a product, a distinct product of 2 numbers, right? Which makes it composite, right? So 2 distinct factors, we got 2 distinct factors greater than 1, right? Now, of course, 78 can be further broken down, so we'll have more than 2 factors. Yeah. So therefore, this is composite. Once again, 7 times 6 times 5 times 4 times 3 times 2 times 1 plus 5. Once again, if you look at these two terms, we have 5 common. So let's pull 5 out. Okay. Now let's write the product, that is 1008 plus 1, which is 5 times 1009. So once again, we whatever this number is, we have 2 distinct factors greater than 1, and of course the number itself. So it has more than 2 factors. Right? So once again, this number is composite. Yeah. Okay, great. So these two are composite numbers. Now let's take a look at a word problem, the 7th question. There's a circular path around a sports field. Sonia takes 18 minutes to drive 1 round of the field, while Ravi takes 12 minutes for the same. Okay, so there is apparently a circular path. Okay, that's a horrible circle. Let me try to draw it once again. So there's a circular path. So Sonia takes 18 minutes to go around the field, right? 18 minutes. Okay, and we have Ravi who takes 12 minutes, only 12 minutes to go around the same field. okay, and come back to the same starting point. Okay. So suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again, right, at the starting point? Okay, interesting question. So the question that they're asking is, after how many minutes will they meet again at the starting point? So this is, if you analyze the time taken by Sonia to reach the starting point again. So Sonia is taking 18 minutes to go one full circle. So to come back again to the very same starting point, it will take another 18 minutes. So it will be multiples of 18, right? 18 times 1 to complete one lap, 18 times 2 to complete another lap, 18 times 3 to complete another lap, right? So they are multiples of 18, correct? They're all multiples of 18. And similarly for Ravi, to reach the starting point, he is taking 12 minutes. Right? Ravi is taking 12 minutes. So it will be multiples of 12. 12 times 1, 12 times 2, 12 times 3. So it will be multiples of 12. So when will they reach the starting point again? When will they meet again? If they have to meet again, we should take a common multiple, right? Which means we are supposed to take the LCM of 18 and 12. Now, 18 is 2 times 3 squared, right? And 12 is 2 squared times 3. So LCM will be the greatest power of each, the product of the greatest power of each prime factor. So for 3 it is 3 squared, for 2 it is 2 squared. You form the product, 4 times 9, which is 36, which was kind of obvious because we already saw the answer over there, yeah? 36 minutes. So they will meet again after 36 minutes at the starting point. Okay. Okay, so exercise 1.1 is over. So let's do a quick recap of what we learned in this lecture. So we learned the fundamental theorem of arithmetic, which says that every composite number can be expressed as a product of primes, and this factorization is unique, right? Yeah. So the prime factorization is unique except for the order of its factors. Okay. And we learned about the definitions of HCF and LCM. HCF is the product of the smallest power of each common prime factor. LCM is the product of the greatest power of each prime factor. Okay. And for any two positive integers a and b, the product of the numbers is equal to the product of their HCF and LCM. Okay. So that's it. So let's wind up the class. We shall meet